pleasure to welcome Dr. Arthur Levy from the University of Nantes, who's going to discuss the work that we did together when he was a Benjamin Meeker visiting professor back in 2018. Just a little bit of housekeeping notes. The way we're going to run the Q&A session is if you want to pop a question into the chat, feel free to go ahead, or you can raise your hand towards at the end of the session. So we're going to have the presentation followed by a question and answer session at the end. So with that, I would like to hand the microphone over virtually to Arthur and talk to us about manufacturing processes for sustainable composite materials of the future.
Well, thank you, James. I'm gonna then start my presentation. There we go. So you should be able to see my slides now, I hope. I'm Arthur Levy from University of Nantes, and I will present you today different parts of this collaboration we have with James. We've had for 10 years, more or less, a little less. So what I suggest is to follow this outline. So first I'm going to do a little introduction, so you know who I am and who James is and how we met. Then I'm going to focus on the Benjamin Meeker program, the one I was awarded in 2018. I will follow that with a public lecture about the composite materials manufacturing. This is addressed to non-engineers. And the last part of my talk is going to be more specifically a scientific presentation of what we did together when I was here. So as an introduction, well, this is me, Arthur Levy. This is my colleague, James Kratz. But as we have the videos on, you see more recent pictures. You see our faces as they look today as well. And maybe I start with myself. So I grew up in Paris. I was born and raised in Paris. Then I moved for my studies to Nantes, which is in the Western France. I got my PhD there, I graduated there. Then I moved to the US for a postdoc in Delaware for 2 years. I moved to Montreal for 2 years. This is where I met James. And then I came back in 2014 and I got a faculty position in the University of Nantes, this city where I am still now. So it's been over 5 years that I'm in Nantes now. As a faculty. Just a little detail about Nantes is a city that's very similar to Bristol in the sense, well, it's more or less the same size. It's on the mouth of the Loire. It used to be, well, it was born with slavery in a way. So I'm sorry, we have to admit that it's very similar to Bristol. And then there was a lot of shipyards. There's a nautical industry and then aerospace industry. So it's kind of similar, and it's very trendy now. So all the people from the capital city try and move to Nantes, just like Bristol, I think. That was my understanding in 2018, at least. Maybe, James, you want to take over to talk about yourself quickly?
Sure. Well, I'll quickly follow that up and say that I was born in Ottawa, Canada, so on the furthest eastmost part of this map, and then moved to Montreal for graduate school. That's where I met Arthur. And then about 8 years ago, I moved to the University of Bristol, and I've been appointed as an academic lecturer in 2017. And I can confirm that people are definitely moving out of London and driving house prices up in Bristol. That's
the same in Nantes.
Okay. Well, now that we have that, let's talk about making airplanes.
Yes, sure. So we met in Canada in 2013, and when I was a postdoc there, I realized that I had some skills that were very complementary to those of James. I have a mechanical engineer background, but I'm more specialized in modeling and simulations of forming processes, whereas Jim has an aerospace engineering background, and he's very good at experimentation, in situ instrumentation, measuring things inside the manufacturing processes. So we are both working with composite manufacturing processes, but with very different skills that we gathered together and were able to do a first collaboration in 2013 on a specific process of, as you see, sandwich structure manufacturing. So this ended up with a first paper together in 2013. So that was the beginning, and then you see that the collaboration went on. So James moved to Bristol, I moved to Nantes in 2014. So for a few years we kind of split apart, but then we met again in 2016. I came to Bristol for a week. A year later, James came to Nantes for 2 weeks. And then I came as a Benjamin Meeker professor in 2018 for 3 months, and that's what I'm going to talk about later in the following. It's still an ongoing collaboration because after this Benjamin Meeker Award, we initiated a dual award PhD program, and we currently have a student who's enrolled in a PhD program as of 2019, Adam Fisher, and he's gonna come. So he started in Bristol for a year. He was supposed to come last year to Nantes, but he's gonna come this autumn for a year in Nantes. So it's really a joint PhD. Let's go to the second part of that talk, now that we're introduced. That's about this Benjamin Meeker Distinguished Professorship Program. The idea here is that I was able to come and visit James. So we had to start, we had to enroll in this in this BM program, and it started with a preparation of a project. So we wrote down a 4-pager project when James came in 2017. We discussed this project a little earlier, and we planned my move in summertime. So I came in May, June, July. That was a 3-month stay, and that was done at the end of the academic year. So I was done with my teaching in France, and I was able to come. That was easier for me as well because, well, I have teaching in France during the scholar year. The award included the travel expenses, the housing and per diem, and this is very similar to what we have, for instance, in the University of Nantes, because when James came in 2017, he was awarded a program as well, a similar program in the University of Nantes, where we paid, well, my university paid for the travel, the housing, and per diem. So it's also similar between the two universities. What we got out of this 3-month stay is, well, first of all, I was here for 3 months, and I was really a faculty member of the University of Bristol. So I had exactly the same status as faculty. I participated in the supervision of postgrad students. I developed a software during that work that's the property of the University of Bristol now. And we had some publications as well. So I presented we presented 2 conference papers. I gave some seminars locally at the laboratory, the Axis laboratory. I gave some industrial seminars with the industrial partners, and I gave a public lecture as well at the Aerospace Bristol Museum, which was very similar to what I'm going to present today a little later. My stay ended up with a journal paper that was also published in a year later, along with a data set which is hosted on the University of Bristol repository. And as I said earlier, this stay was also the initiation of the dual award PhD that's currently running. Besides these facts, in terms of professional facts and administrative facts, of course, that was also a family experience, because back then we were 4. We're 5 now, but I had 2 kids and my wife, and they followed me during this summertime. So that was also a great family experience. You probably recognize Bristol here, the Concord here, and some other places we visited in the UK during this long stay, this long summer, 4-month summer. Okay, so let's dive into the public presentation part of my talk, which is talking of manufacturing aircraft of the future, hopefully, with composite materials. So we're going to talk about composite material and sustainability. I will start with a little bit of material science. And the idea here is, well, first of all, what are we talking about when we say material? So a material is something that that was crafted from matter. So matter would be the soil, and you get some brick that you can use industrially, or you can craft by human. Timber would be obtained from wood, of course, from trees, and all this matter gives material that have specific properties that are useful for the engineer. Typically, if you're building an aircraft, the question now is, you need specific material. You're going to choose some materials that are adapted to your aircraft. So what's the properties you need for your aircraft to be efficient? Well, the properties for an aircraft that you need a material that's light, of course, because you're trying to fly. You need it to be strong, meaning that it will not break when you apply a force on it. And you need it to be stiff. It's a little different. You need it to be stiff. Stiff means that it will not deform when you apply a force on it. For instance, the rubber is not stiff because you can definitely deform it when you apply a tension on it, but it's pretty strong because breaking rubber is hard, you know. So you have two different properties here. And finally, you want it to be cheap, but it's more the industrial partners that are going to deal with the price. I mean, we're dealing with the scientific part of it. So the weight, the strength, and the stiffness. And one way to choose your material adapted to a given application is by following a specific procedure that was developed in Cambridge by Professor Ashby, which is very standard now in the field of material science. And one way to choose a material is by using these Ashby graphs. So here, we're going to plot a map, let's say, where, for instance, you're plotting the density on the bottom line, and you're plotting the strength on the vertical line. So basically, you're going to have density means you're going to have all the heavy materials on the right and light materials on the left. And you're going to have all the weak materials on the bottom and all the strong materials on the top. And you can plot all the known materials. So typically, this is what it looks like. You see that here on the bottom left, you have foams, so very light materials, but very weak as well. And on the top right, you have all the metals in red. The metals are pretty heavy, dense, but they are also very strong. So ideally, to fly, you would like something very light, but very strong, yes. So you would like something here. And luckily, there's no material, there's no ideal material. And nonetheless, you can see that some of these material around here are really almost as strong as the metals, almost as strong as the steel, for instance, which is around here, but really lighter. I mean, it's almost 10 times lighter. And these guys are carbon fiber reinforced plastics. So this is a composite material these are the composite material we're going to talk about today. So what's a composite material? It's a material made of fiber, so carbon fiber, meaning a textile, like the one you see here, mixed with a matrix, typically a polymer matrix, a resin, it could be epoxy, it could be thermoplastic, thermoset resin, and you mix them together and you produce a laminate. So here, typically, you see a micrograph of a laminate where you have different textile and different plies of textiles with different orientations. So here we see the fibers that are along this direction, whereas for this layer, the fibers are perpendicular to the screen. So you can orient also your fiber in the direction you want your material to be stiff or strong. Now the question is, well, how can you actually produce such materials? Before producing them, I wanted to finish about the composite material in the aircraft and show you that the composite materials are more and more used in flying structures. So you see that in the 70s, 80s, that was below 5% usage of composite in flying objects, whereas today we're hitting with the 787, we're above 50% of composite. So here, typically, you have the 787 Boeing, and you see all the gray parts are made of composites. So it's really a bigger and bigger amount of composite in these flying structures. So now, okay, we want to use these composite structures. How are we going to make them? Because the question is, how can you mix these fibers and this resin and make a structure that's actually usable for a given application? So I'm going to do a little bit of history before and switch back to other types of materials. So if we're looking at ceramic manufacturing, for instance, well, you know that ceramic has been used in the history for over 20,000 years. I mean, it comes from the Neolithic first. Then industrially, it has been developed for well, 200 years industrially, and it's still used. And well, that's the space shuttle, so it doesn't exist anymore. But on flying structures, you still have some ceramic at some points, at some locations. And you see that ceramic is pretty well known. I mean, we've been using them for thousands of years. Metal manufacturing, another class of materials, well, it comes back to the Bronze Age. So it's also around Neolithic, and we have cast iron 200 years before Christ. So it's a couple of thousand years that metal has been used industrial. Well, industrially, it's more around the Industrial Revolution that we use steel structure a lot. But still, I mean, this is a well-known metal manufacturing has been used for years. It's still used in flying structures. Well, once again, the Concorde doesn't fly anymore. So, but still, it shows that we've used it in the 20th century. And here you see, well, metal manufacturing, let's say around 2,000 years. For plastics, well, plastics, maybe the first plastics was the rubber, you know, all these, the Macintosh. That dates back to the industrial, a little after the Industrial Revolution. We have celluloid in the late 19th century, and we have during the 20th century a lot of plastics as well. Let's say it's 200 years old. Now, if we're looking at composite materials, meaning something made of fiber and a matrix, well, of course, we have some old style composites like papier-mâché, which is of course a fiber and a glue. But if we're talking about more industrial usage of fiber and plastic, you know, it dates back to the early first part of the 20th century. And concerning like industrial flying object, it's more like the 40s. So this is something that's 50 to 100 years old. So it's really recent. Composite manufacturing is really recent, and we are still struggling with making good parts and understanding what's happening in this structure when we are actually trying to manufacture it. Indeed, mixing fiber and the plastic together and getting something that's perfect, let's say, is very difficult. Very difficult. How are we going to do that? We want to mix this plastic and these fibers. We have plenty of different ways of doing it. We can press, inject the plastic inside the fiber, put that into a press, do thermostamping, oh, that's in French, I'm sorry, do tape placement processes. What I'm going to talk about today is one specific process, which is called liquid composite molding. So the idea here is that you take your dry textiles, and you lay them up. So you do your stack of textile. You put that gives you your preform, your dry preform. You put the dry preform inside a mold that you close down, and then you inject the resin, so the plastic, inside the mold, and hopefully the resin is going to flow inside the porous material and fill the mold and make your part, your mixture of fibers and resin. This is a typical composite manufacturing process. So now I guess the question is, how can we meaning academics or faculty staff, help with manufacture in this field of composite manufacturing? So when we are trying to do this and we manufacture structures, we realize we can have a lot of defects. We can have, well, we can burn. Here it's a tape placement process I was talking about quickly, but here you see that we may burn the material, so this would be a defect. You may have some voids, so you tried to put your resin inside your material, but it didn't go everywhere. There are some dry spots here. There's a big bubble here. This is a micrograph of a structure here, and you see that you have defects, you have bubbles, and this will be a weakness in the final structure. You may try to do L shapes, and you see that the flanges here have a given thickness, and the thickness in the corner is really thinner. So there's also a weakness here in the corner. So it's more of a geometrical defect here. You have some residual stresses. So you're trying to manufacture a flat plate, and luckily it comes out not flat at all. It's really a banana shaped plate. So this might be a defect. You might have also all these textile layers that may slide and make some wrinkle and have some defects inside your stack of layers. So we try to avoid that. And one way to avoid these defects would be, well, one, let's say basic way, time-consuming way would be trial and error. Try to, in this case, for instance, try to reduce the power because it's burning, and you make a new part, and now the part is not well, the composite is not sticking well, so you have to increase the power, and then you decrease the power, you go slowly, you go, well, this could be very time-consuming and very expensive in terms of material because you're doing a lot of experience to find out how we can actually manufacture this part without defects. The other way of doing it is try and predict the physical phenomena that occur inside the material during the manufacturing. So we're going to try and write down the equations of motion, of the fluid flow, heat transfer equation, burning equation, so kinetics of degradation, stuff like that. So this is really a physical modeling that you're doing with your pencil and your paper. You write down equations and you understand, then you're trying to predict what's happening. These physical equations are going to call for material properties that you have to characterize in the lab. And once you have all these properties along with the equations, you can solve the equations. So typically you're going to solve that with a computer because these are difficult equations. So you need a computer, numerical methods, and you're going to solve that your equations with simulation tools in a way. And now you have a predictive tool inside your computer. So it's cheap. You can run it several times. Well, before running it several times, maybe you want to validate that. So you're going to compare what you're doing in your computer with the real. So for instance, the temperature you're predicting with your computer, you're going to try and compare it with the temperature you measured with a sensor, so a thermocouple inside your material during one experience. So it's only one validation experience. And then you're happy, you say, oh, my model is predictive. So it's pretty good at describing the reality. We are happy, we can use this simulation and run it several times and get some industrial results. So this is the classical scientific approach we're following. And just to illustrate that, I have a very, let's say, a first example, a test case here for this scientific approach. And I wanted to focus on the toaster. So imagine you want to build, you're a toaster manufacturer. You want to build a toaster that will toast the perfect toast. So of course you don't want this, and you want something that's perfectly grilled but not burnt. Let's try and follow this this approach. So what's the physical modeling? Well, you can say that the perfect toast will require a given amount of energy. So the quality of the toasting quality is going to be proportional to your energy. The energy is going to be the power of your toaster times your time. And the power is going to be, if you consider that there's a heating element that's a resistance, it's going to be the tension times the intensity. So this is tension times intensity, sorry, and the intensity will be given by the resistance, and this is the Ohm law. So typically, with a few equations, you can describe the quality as a function of the tension, which is 240 volts in the UK, I think. Or is it 220? It's 220 in France. I think it's 240 in the UK. And the resistance of this heating element that's inside your toaster. So you see, it's calling for property, for given data, 240 volts, but it's also calling for a material property, the resistance of your heating element, and you have to characterize it. So characterizing the resistance, you're going to put a ohm meter and measure this resistance. And now you have a fully predictive model that you can solve. So you're going to solve that, do the multiplication, and obtain the quality here. So here it's pretty easy. You're going to use a calculator and do your division here, your multiplication, pop up the product, and get the quality. And you can predict the quality. Of course, you also want to, once you are predicting the quality of the toast, you want to validate that you're good. So you're going to do several tests with different times, for instance, and predict and check that what you're measuring as in terms of what you're predicting in terms of quality is representative of what you did in your toaster during your experimental validation campaign. If you're happy, then your approach works out and you have a predictive tool and you can use it. You can use it to help the manufacturer of toaster. For instance, you can plot a graph of the quality of the toast versus the resistance of the heating element. So now the manufacturers can say, oh, I want a 50% burnt perfectly grilled toast. So I need a 200 ohm heating element to put in my toaster. So that's one illustration of the approach. And what I suggest is to switch to the last part of my speech, which is about how we applied this approach to a more scientific scientific case of composite manufacturing. So it's about what we did together with James when I visited Bristol. So the contest of me coming to Bristol in 2018, we wrote down a project and tried to reduce. We thought about sustainability of these composite parts. So the problem, one of the problems when you're manufacturing such composite parts, is that you're cutting some textile with a shape that's going to be the shape you're going to use in your final part. So here, for instance, a ring. And unluckily, you have a lot of waste because you see all the outside part here is going to be the ply cutter waste. So that's a shame. We have to make something with this ply cutter waste. One way to refurbish this ply cutter waste is to shred them into a big shredder and create a reclaimed material. So that's a mat. We kind of align all the fibers. So these are carbon fibers, and this is pretty high-tech material. This is really aerospace grade fibers. So you don't want to waste them and just dump them. That's why you're shredding them and try to do a reclaimed material, but still with high quality fibers in there. So these rolls, these reclaimed material rolls, are something that you can buy commercially. And the question was, how can we actually make a part with this reclaimed mat that we obtain, that we can buy commercially? We decided to try and process it with the classical manufacturing process that I presented earlier, the liquid infusion process. So here the process is the same as the one I presented. This is called resin transfer molding. So we put a preform inside the mold and inject the resin so that it fills the mold and hopefully makes your part, your composite part at the end. The problem is this material, this reclaimed material, looks very variable. You see, it's the fibers are really randomly distributed in the roll here. So you have something that's very variable, and it looks poly oriented. And what we found is that if we inject resin from one end here and hope that the resin flows and fills the mold homogeneously until the end, well, this is not true. The flow front is going to be variable, and you're going to have some spots that are going to stay dry before some other spots are the flow is going to go faster. So here you see that at the end, the flow reached the end on this part, but there's still some dry spots on the end. So we need to monitor this flow front. There's really a requirement to monitor the process. One way to monitor this process of resin infusion inside the preform is to put some pressure sensors. And that's what we did during my 3-month stay. We used this commercial pressure sensor instrument. So this is a film made of almost 2,000 cells that we barely see here, but there's a lot of cell here, and this gives the pressure at each location in this 10 centimeter by 10 centimeter film. We're going to put that inside a mold and try and see what we can do with that. So typically what James did when in Bristol is building a mold. So he put a flat plate, he put the pressure sensor in here. We put the reclaimed material, so a disc. We chose to use a disc, circular geometry. We put it on the sensor, and we close the mold with a lid. And it's a transparent lid in plexiglass, so that's pretty cool because we can see, you see in the next slide that we see the resin flow. We're going to inject the resin from the center, and it's vented on one side. And you see that here, typically, with a video, with a camera, you can see when we inject the resin. So here we took some golden syrup just for the test case in the lab, and we injected some fluid, and we see the dry part of the preform and the wet part of the preform. So we can see the flow front. If we do some image analysis with a computer, we can actually identify this flow front, which is an ellipse in this case, and this gives some information visually, some information on the flow front location. At the same time, and we are here working on the experimental part. You understood that, I hope. At the same time, we put the pressure sensor inside the mold. So the preform was a little bigger than the pressure sensor. So here we have only half of the pressure, half of the disc geometry. We have the vent here, so the place where the injection gates are here, where we're going to inject the resin. And you see that the pressure inside the mat before we inject the resin is very different. Some places you have high pressure because there's a lot of fiber. There's a high pressure here because there's more fiber, and there's less fiber here, so there's less pressure. It's a very variable distribution of the material inside this mat, this reclaimed mat. This is going to influence the flow, and we can measure this pressure map while we are injecting the resin. And by doing a little bit of math and subtracting the dry pressure, the dry mat pressure, we can obtain the resin pressure. And you see here, this is the map of resin pressure, and this gives actually a very good prediction of the flow front, which is the ellipse that we actually saw at the same time and validated with the camera and the transparent lid. Meanwhile, what I did when I was here was working also on the numerical simulation. And the idea was to start with this random distribution of pressures that is representative of your material, and trying to account for the fact that this high pressure here means that there's more fiber, so it's less permeable. Whereas here there's less fiber, so the resin is going to probably flow easier. The flow of resin is going to be easier here than there. We did that by solving the equations of flow. And I'm going to skip a little bit all the technical part, but if you want some details, this is all in the published paper. So we took into account the compaction curve, this dry pressure map that I just gave you. We can obtain the fiber volume fraction. The fiber volume fraction can give us the permeability map, and the permeability map can be used to solve for the flow. So the equation of flow, which is called the Darcy flow. This is the flow of a liquid inside a porous material. We solved that numerically inside a computer. So you see here the typical plots that the computer can give. So this this compares well to the pressure sensor measurement that we had previously. And if we compare what the finite elements, so the numerical method gives us in terms of flow front, so this is the red ellipse here, this is very predictive. This is very similar to what we observed with the camera And this is a little better than what the previous models would have given us without taking into account the heterogeneity. Okay, I'm going to conclude on this scientific part. The main contribution of this scientific work was that we, of course, worked with this reclaimed material, and we showed that it was variable. The variability was shown to affect the flow while we were infusing, so we have to control this variability to be sure that we don't have defects and trapped air, for instance, at the end. And we also developed a simulation of the infusion that enables us to predict what's happening during the infusion. Okay, I guess I'm finished with my presentation. I'm going to conclude with one slide of perspectives and challenges. I guess one thing that we have to work on in terms of composite manufacturing for aircraft is to try and orient the thing towards sustainability, of course. So we saw that there's some waste because of the production. There's production waste, and one way to address that was by minimizing the waste or reusing all the waste, and this is what we did during my Benjamin Meeker stay. There's also a big issue that I didn't talk about, but we're using fibers mixed with resin. So at the end of life, and here you see a typical picture of an aircraft cemetery in the US. There's a big question, which is what are we going to do with all these materials which are mixing fibers and plastics? So a big issue and something that we should really work on in the domain of manufacturing is the recycling. I guess another domain of current challenges is the online control. So I mean that during manufacturing, if you could control very well your process, you would have no defects in your materials, in your parts at the end. That's what I tried and showed you. So if you have no defects, then there's no scrap. And that's better for sustainability, of course. And finally, last domain, which is maybe a little less talking about sustainability, but it's something that's really important for a manufacturer of large parts. So, you know, wind turbines or aircrafts, we're talking about dozens of meters long structures. So here, one big challenge in terms of composite manufacturing is the production of very large parts and assembling techniques to produce large parts. And this is actually something that we're dealing with Adam Fisher, the PhD that we're supervising with James. He's working on an assembly process. So I'm finished with my presentation, and I hope that you have a lot of questions. James, you can take it.
Thank you very much, Arthur. I'll open up the floor to any questions that anyone might have. So there's two routes you can take to ask any questions. That would either be in the chat box, or you can raise your hand by clicking on the reaction button, raise your hand, and then unmute yourself to ask any questions. So while people are thinking of their good questions, maybe, oh, we've got our first one, so they don't have to put me on the spot. So we have a question from Adam Smith, and the question is it possible to incorporate a confidence parameter into your finite element model to account for the high variability in the reclaimed preform structure or permeability?
Sure. So the idea here, maybe I didn't want to go into too technical a presentation, but I'll still show you, let's say here. So the idea here is we're not even including the variability because we're measuring locally, thanks to the pressure sensor, the property locally. So it is variable. When you look at this map, it's already variable, but we know the exact value at each location of the pressure measured when we close the mold. And this pressure map can be transferred into a material property map. So typically, I skipped quickly, but the compaction curves and the dry pressure map that we measured gives a fiber volume fraction map. So the fiber volume fraction map gives a permeability map. So we really have locally a property that's a field, that's variable. So we are taking into account the variability by solving at each location using a property that's varying at each location. I don't know if it answers the question.
maybe I'll stretch it a little bit further. So I mean, that is the direct solution to the real problem, but potentially you might end up in an environment where you're actually unable to measure your preform directly in the mold. So I guess you could stretch the concept and think about how could you account for variability in the FE model, possibly through the use of stochastics or even just like normal distributions. Is that a possibility?
So yeah, so that's also something we're investigating with our PhD, our joint PhD. So Adam Fisher is currently working on stochastic FEM methods. The idea indeed is to account for variabilities in properties or loading and see how this transfers to variabilities in the output of your model. If you're willing to chat with Adam, you're more than welcome to pop me an email and I'll put you in contact. Oh, plus you have the same first name.
Well, while we're waiting, we've got a few more minutes, and while we'll see if there's any other questions that come up. Maybe I'll ask you a slightly more generic question: is what were you most proud of your stay during your stay in Bristol?
That's a good question. Well, I guess I think personally first, that was a great experience for me and my family and my English, because that's always good to practice your English, you know. I mean, I was in the North America for 4 months, then I came back to France and I completely lost my English. And then I moved for 3 months, so it was good for the language. It was good for the personal experience, definitely. It was professionally, I think that was also interesting because I guess UK has a border with the Europe. Well, now I'm sorry to say so, but this is pretty true now with Brexit. But that was historically, we don't know the community of British people that work on composite manufacturing. These are two very separate community, and I was able to meet a lot of people that I didn't know well before. So in terms of meeting the community and going to the local conference, ICMAC in Nottingham, I think that was a professionally great experience.
Okay.
What about you, James? May I ask the question to you then? Of me, what's the best experience of me staying with you for 3 months?
I absolutely think just the opportunity to bring a different perspective into a problem that we were already tackling, and being able to bring in the numerical side of things that can help stretch the experimental campaign to a place where we can explore the parameter space much further. It's always useful. It was also a very nice, example of how digital manufacturing can actually work, in the sense of measurement, simulation, verification, all in one integrated system. So that was quite nice.
I remember that's a domain that the NCC was very willing to investigate, to dig into as well. So, well, the industrial partners were also encouraging, I would say, on that aspect.
So I realize we've got about 2 minutes left in our webinar. If there's any final questions that people would be interested in posing, now would be a time. Otherwise, is your email address on here somewhere, or are you Googleable?
Maybe
I know sometimes
it's not. So I'm very bad.
You are.
Up. There we go. I'm Googleable. probably if you type Arthur Levy Nantes, you should have
You're
it.
also on LinkedIn.
I'm on LinkedIn. And I think the international people would like to put back the general slide for the festival with the link to the festival, the link to the festival. Yes, I think
So I believe it is recorded and it will be posted somewhere.
Perfect. There we go. Perfect. So you can also definitely contact the people from the IRP and they will forward to me any questions. Contact. How can someone? There's another question I'm reading.
So how can someone do a JV or partnerships?
What's JV?
I'm not up to the language on JV.
Benjamin Meeker, what I did or what's JV?
Joint venture normally.
Oh. When you mean joint venture, do you mean commercial activity? Or when you mean, because
so the collaboration currently is between two universities, so this is purely academic. How would you address that? So in terms of collaboration, we have this joint PhD that's ongoing. We have, but in terms of commercial activities, I don't know.
Well, I guess when you think about the commercial outputs, there's the intellectual property that was generated, which is the know-how of how to use the sensors, how to characterize the material, the software that was created, and that can be discussed with the commercialization offices. And there are a variety of options that I'm sure both universities have to engage with, companies, whether it be through the support of doctoral programs, so engaging with postgraduate researchers, knowledge transfer partnerships. There's a whole host of activities. It could even include direct consulting.
We also have this spin-out company we are working with closely at the University of Nantes. So for commercial activities, we refer to them. And there's another question. So I use the FreeFem++, which is a scriptable finite element. Sorry, I'm going to read the question. Hi, I just wanted to know which FEM software you've used for this work. Thanks. So I've used a French library called FreeFem++, which is a scriptable finite element solver. And the script is available alongside with the article, actually, if you want to run the simulation that you have just shown. It's available. So there's a .edp file that you could run with this open source software called FreeFem++. Just refer to the paper, and maybe I'm going to put a link to our paper. That would be perfect, right? Maybe how up.
Correct me if I'm wrong, or is it Darcy flow?
It's Darcy flow, yes.
Okay.
Except that it's locally, you have a field of permeability, so it's a little tricky. You have to project the field that you measured with your sensor onto the numerical mesh, and it's a little tricky. So I'm gonna just put the link, and if you wanna access, this is to the article, and alongside with the article, there's the script and FreeFem++. But please feel free to pop me an email again if you want some technical detail.
That's actually quite an interesting concept of being able to import the sensor output directly into the finite element model.
It's a direct numerical simulation. So we import this map that we measured with the sensor and project it on the numerical mesh. You saw that this numerical mesh, actually, it's very numerical. It's like triangles. Great.
Okay, well, I guess that's bringing today's session to an end. So thank you, everyone, for joining. And if you have any questions, feel free to get in touch with Arthur at the University of Nantes or myself at the University of Bristol. If for some reason you're an academic and you're interested in visiting the University of Bristol, if you Google the Benjamin Meeker Visiting Distinguished Professor Scheme, so that's up 1 to 3 months. There's even shorter ones as well. So, hopefully the world will be returning to, more international visits soon, or even just leaving the house. And we'd be happy to welcome you into Bristol to work with us.
Yeah, the international office was very arranged. That was really a great experience, and they handled that perfectly. Thank you. I would like to thank the international office for the experience I had 2 years ago again. So thank you all. Excellent.
So I guess I'll hand it over to you, Lauren, to end the session.
Okay, great. Thank you very much. So thank you both for a really, really fantastic presentation. It's not remotely my area of expertise, but I found it really interesting. So that's hopefully a big compliment, because it's not just for the specialists. So that's great. We really, really appreciate you taking part. And just to say, we do have other events in the showcase taking place this week, so check out our website. And if you are interested in potentially coming to Bristol to partner with our researchers, not just on this subject area, but any, it's open to all schools, all faculties, all theoretical and methodological approaches, then check out our website and get in touch. And obviously you can't come at the moment because of the travel restrictions, but we do have an online collaboration award scheme as well. So if you want to kickstart a potential future collaboration, check out our web pages for that and see what you're able to do now. And hopefully we'll be running schemes later in the year for visits in 2022. So check out the links on the chat window and on the slides here. And we'll also have a recording of this presentation up on our website. If you got caught up or joined late, or you want to share a link with colleagues who you think might be interested, come to our website in a few days' time and we'll have the recording up there. So that's everything from us. Thank you again to both of our speakers today and for a great session. And yeah, hopefully see you in Bristol soon.